Good morning, everyone. Can you see my screen?
Yes.
Okay, so today I would like to present this paper, which title is Design and Modeling of a Microfluidic Coral Polyp Culture Chip with Concentration and Temperature Gradient. So here the authors propose the characterization of this chip, and they study, they solve numerical equations so that they know how it forms these gradients for the temperature and for the concentration. So they created this chip in order to study the polyps and corals, because as you know, when coral and polyps are exposed to different temperatures, they start bleaching, and so they propose this model in order to study this behavior. So here is a picture of the coral and coral polyps. There are a lot of microorganisms that live there, so that's why it's important to study how they damage with the temperature changes. So they propose this microfluidic device. As you can see, it consists of 3 layers. So the top layer has the reservoirs. Here you see the radio of each of them, and the outlets. Here are also the culture chambers where the coral polyps are going to be cultured. In the middle layer, you can see the serpentines. So they form the concentration gradient. So here they are going to mix two substances, and then with this concentration gradient, they will produce different mixtures and different concentrations of these two substances. The last layer is the bottom layer, which has a copper circuit, and that is how they produce this Joule effect, so to heat the substances. And it's also important to mention that here the chambers, they have a dentate part, so that this dentate part will improve how the heat dissipates, and also the dentate part is going to fix the coral polyps. So here we see how they solve the equation. So this flow of the flow and also the mass and the momentum, they are going to follow the energy conservation equation, and they study also how the substances diffuse, how they mix, and this is how they produce the Joule heat. So they measure the heat that is generated by the circuit with a potential difference between the two ends of the circuit, and also the distance between these two ends of the circuit. So they list here the material properties. This chip is made of silicon glass, and here you see the electrical conductivity of silicon glass and also copper. So that's how they made this heat gradient, the temperature gradient. So here we see the flow field simulation and how they place here two substances, and after 3 mixing stages, then here you have the concentrations that they reach in each independent column. So these chambers are going to be independent, and they also model the flow, the velocity, and you can see here the flow enters to this chamber and how it enters. So here you see the distribution of the velocity. Okay, and also the dentate part contributes to form a turbulent flow just here locally in the chamber, so that the solute is transferred to all parts of the chamber. So it makes it increases the time of residence there. They also measure the flow velocity at each column, and here we see how they found the best range temperature to work with. So they control the potential So, for example, with 2 volts, they reach this range of temperature from 22 degrees Celsius to 30. So that was the best range of temperature to work for these polyps, for these polyps, okay? But if we increase the temperature to 3 volts, then the temperature reaches too high, 36 degrees Celsius. So that is going to be the temperature in which the polyps will bleach. So that is also a good model to study the bleaching of the polyps. And the rest with higher voltages, they are not going to be used because if that's too high, that will damage the polyps. Okay, so see here we see this heat map, the temperature profiles of each of the chambers and each column. And also they saw how the material will behave with this temperature. So the deformation is expressed here with the stress, these von Mises effect stress caused by heat. You can see here the simulation, and also they measured the displacement caused by the heat, and they found that at this corner the displacement is the highest. It was 8 microns. So they proposed these chips in order to study the effect of the temperature and also of the gradient concentration to study the polyps. And they haven't cultured the polyps yet, but now they have the microfluidic device, so they are ready to use it in further experiments. Okay, thank you. Do you have any questions?
Thank you, Anita.
You're welcome.
I don't have any question, but I have to say that I think it's very beautiful paper. I think they think a lot of the design and the effects of the deformation of the material too. That was very important, no?
Yes, I was impressed that they haven't cultured the polyp yet, but they have thought about many of these parameters that will influence the polyp behavior.
Yes, it's very interesting that the graphic that you are showing now in that corner, no? I was thinking that was the cooler part of the chip when you start to showing us, but then I don't understand how the resistance of these copper filaments are working, no? But it's very interesting. Well,
Yeah, it's the silica, the material of the chip is the one that displaces a little bit when you increase the temperature. But this displacement is not significant, so it will not affect the experiment.
very well, very well. Thank you. That was interesting to answer. Who wants to follow Anita?
I'm the next one.
Perfect.
Okay. Can you see my screen?
Yes, Andrea.
Okay. Well. Today I will talk about of this article called high throughput sorting of eggs for synchronizations of C elegans in a microfluidic spiral chip. To realize different experiments, it's important to use worms in a specific stage. For these reasons, the synchronization is necessary. The ordinary techniques use chemical compounds to kill adults and leave only eggs. However, that could modify the posterior worm behavior.
Andrea, we can't hear you.
Here. In this paper, they use
Sorry,
a
Andrea,
device
we lost
for
you
sort analysis.
a few minutes. The last thing we are listening was about the.
Sorry, my connection is.
Yes, I know.
It's a little unstable
Mm-hmm.
in this moment.
Well, try and go on if you can.
Can you hear me now?
Now, yes. Yes.
Yes. Okay. So they use a microfluidic device with this spiral shape for sorting and mix egg worms populations. Each larval stage shows varying cuticle positions and different forms of plasticity in the organism nervous system. The spiral chip use inertial lift and drag forces to extract eggs within a microfluidic spiral channel. The incorporation of curvature within inertial system results in a generation of cross-sectional drag forces perpendicular to the flow direction. These, known as the Dean drag forces, cause particles move within a secondary vortex. The combinations of these
Andrea, we lost you again.
forces result in the
Sorry,
focusing of
Andrea, we
particles
lost
to
you.
a lateral. Okay. Can you hear me now?
Yes.
Okay. The trapezoidal cross-sectional channels have been proven effective to widen this distance between equilibrium positions, as demonstrated in separating circulating tumor cells from the blood of patients with cancer. As can be seen here, the channel width and height is 1,000 and 116 micrometers in the other side, and 220 micrometers in the inner channel side. Trapezoidal cross-sections with deeper inner wall results in stranger vortices in the inner channel side relative to the other side, with particles between 5 to 25 micrometers being focused in the inner side. The formations of the stranger vortices tends to reduce the impact of flow rate in the sorting. This device has 6 spiral loops with inner and outer radius of 2 and 6 millimeters respectively. So they work with three populations, X, L1, and L4 worms. The first test sample contained a single population. The second one was a mixture of two developmental stages, and the last test sample was a mixture of all three developmental stages. During sorting experiment, the worms concentrations was 7 worms per 10 microliters and total injection volume of 5 milliliters. In this equation, they use these equations for quantify the sorting results. The sorting efficiency was defined as the ratio of the number of organisms, eggs or worms, in the desired output to the total number of organisms collected from both channels. And the sample purity was calculated as the ratio of the number of sorted eggs to the total number of all organisms from the inner outlet. Okay, in the result, a major effect, the major factor to determine the possibility of particle to be focused spiral channel is the confinement radio, that it's applicable to both linear and curvilinear microchannels, and is the radio of the particle diameter and hydraulic diameter. Well, in this figure, again, you can see the curved trapezoidal cross directions. The curvature results in a secondary flow initiated by centrifugal force. The direction of the secondary flow is always towards the other side in the middle of the channels, thereby focusing the organism along the sidewalls. The horizontal component of shear gradient lead force near the inner wall is the same direction as the reverse secondary flow. In the curved channels, hence X approaching the inner wall through the reverse dim flow are also forced by the shear gradient lift force. However, once X reach the inner wall region, they cannot follow the secondary flow anymore as dim drag forces, and it's opposed by shear gradient force. The X focus near the inner region on the other side here, and the worms which approach the outer wall through the secondary flow. And thus the worms retain their focusing positions near to outer wall. And here note that the magnitudes depend on the shape and size of X and worms and are the dominant force components. In this figure, you can see the maximum value of the secondary flow velocity at 9 millimeters per minute. That is 0.14 meters per second, which is much less than the average velocity that the main flow at this flow rate. This difference between the order of the magnitude of the primary and secondary flows impose stricter conditions on the microchannel length, such that suspended objects have enough time for a complete lateral migration. This figure shows the relative high flow rates above 1 milliliter per minute. C. elegans X migrate towards the inner wall of the spiral channel, while larger L1 and L4 worms became focused along the outer wall of the spiral channel. The sorting efficiency for X, it's above 90% on average across the flow rates between 5 and 10 milliliters per minute. In the case of L1 and L4 worms, the efficiency significantly increases. This improvement can be explained by the increasing centrifugal force in the spiral channels, where the centrifugal force and tangential velocity in a curved channel. Compared to L4, L1 worms has a lower sorting efficiency due to its smaller size. Overall sorting efficiency of L1 and L4 worms improved at flow rates above 5 milliliters per minute. When sorting a mixed populations of two different developmental stages, such as eggs and L1 or L4 worms, the worms were sorted out through the outer outlet, while most of eggs were found in the inner outlet and the flow rate of 5 milliliters per minute. In both cases, L1 and L4 were already focused to the outer wall in the last spiral loop before reaching the bifurcated section. Okay. And here, this figure shows the proportional distributions of the X and L4 words within the channels at the inlet. Third and okay. This figure shows the 3D wall plot shows that there is a random distributions for X and L4 worms across the channel near the inlet initially. However, further along the channel and the third lobe, or here, the eggs and worms are focusing towards the inner and outer walls of the channel, respectively. Within this loop, the eggs almost all focus to the inner wall, while the worms are still being focused in the sixth loop. Just before the outlet, two distinct peaks are observed, indicating the focused eggs and worms. These results implies that at least 3 loops are required to observe separations of the eggs and L4 worms. Um, Finally, with the both mixtures, the efficiency, sorting efficiency above 90% was achieved within a flow rate range of 5 to 10 millimeters per minute. In the case of sorting between L1 and X, the purity was 80%, and in the sorting for the sortings of L4 and X, the purity was higher with 97%, probably due to the significant difference in size between these two developmental stages, especially at the flow rate of 6 milliliters per minute, was obtained for sorting X from L1 and plus X and L4 plus X mixtures respectively. In conclusions, the inertial lift force combined with the secondary ding force allowed focusing the eggs along the inner wall of the spiral channels, while worms of larval stage focused out of the outer wall. Okay. Thank you.
Very well. Someone has any question? If there isn't any question, we can follow. Who wants to be next?
I guess it's my turn.
Okay.
Can you clearly see my screen?
Yes, Eric.
Thank you for your confirmation. Well, good morning, everyone. Today I'm going to talk about red blood cell segmentation by thresholding and Kenny detector. So this article proposes an automatic segmentation algorithm for red blood cells that compute the threshold image using boundary-based methods after enhancing the local and global detail using morphological operation to simulate red blood cell in bioimages. As we know, in the medical fields, blood cell testing it's among the most important typical of clinical examination. Needs a computer visual system that can detect, count, and classify cell and bioimages. In this slide, the segmentation plays a vital role in this type of system. That's why a model for cell segmentation algorithm was designed using four basic steps, as you see here. Preprocessing is used to create 2D filters that allow the system to compute the gradient magnitude of the images with the goal of the locally enhance the appearance of red blood cells in the images. At the same time, a proper threshold value in each input image based on its gradient magnitude was generated, and the image into grade scale by the adaptive thresholding method was converted. On the other hand, its age detection process through the operator and detector CANI. After the CANI detector was applied, morphological operators such as dilate and open were used to show lines of high contrast in the image and isolate the full shapes of each segmented cells respectively. Regarding experiments, the experimental validation of this algorithm was performed using all images in the human red blood public dataset available in the BBC. The dataset consists of 5 images data format, as you see here in Figure 1, which are converted to a bit this format before coding. Regarding procedure, this experimental procedure was performed to achieve 2 goals. The first, the same algorithm under different setting was used with the goal is to measure the precision segmentation. The performance of this algorithm was compared in an age detection process, but using CANI and soil operators. And the second goal was to compare the algorithm with 2 typical methods. With the following metrics can be evaluated the segmentation performance of the proposed algorithm. A confusion matrix is a table that is used to define the performance of a classification algorithm. The most frequently used performance metrics for classification are accuracy, precision, sensitivity, specificity as F-score values according to follow this equation, as you see here. At the same time, dice coefficient similarity is used to measure the accuracy of segmentation, and is based on the dice coefficient. And finally, area under the curve. The results are classified based on the goal of the experiments, as we mentioned in the experiment section. Regarding first goal, examine the algorithm proposed TCD under the different settings. The goal was to measure the validity of the age detection process using the soil and CANI detectors. Figure 2 shows how the difference detection operators can produce difference in the precision of segmentation based on the measure accuracy rate of the detected, and it could be found that the soil operator mainly exhibit incorrect age position and loss on cell age. Moreover, the CANI age detection produce greater segmentation accuracy than the method using a soil operator, as shown here in table 1. The second goal compare the TCD with other methods according to according to the F-score and dice similarity, as shown in table 2, the accuracy of the TCD algorithm is greater than the other methods, that the DCU is ICE methods produced by the word segmentation. Results according to the F-score. Furthermore, this table shows that the segmentation of the DCU ICE methods results in slightly lower values than those for the TCD algorithm according to the dice similarity metrics. On the other hand, the UC shown on here in figure 3, we can see regarding image segmentation that the TCD algorithms in green produce a greater ROC than the other two methods proposed. So that's all. Many thanks for your attention.
Thank you, Eric. Do you have any questions? Well, if you want, I have to present my paper now. Do you see my paper?
Yes.
Yes.
Thank you. Well, I choose this paper because I was thinking about to use magnetic beads in the chips, and someone tell me that there is a difficulty with to make the magnetic force field to use it for bioseparation. This paper is magnetic bead separation characteristics of a microfluidic bioseparation chip based on magnetophoresis with lattice distributed soft magnets. Well, they used an experimental platform to observe the capturing of magnetic beads in a build and the capture phenomenon of magnetic beads with lattice distributions of magnet. It's also experimentally verified. Well, this is magnetic beads are interesting to use in our field because they can be attached covalently with any molecular that have amino groups, carboxyl groups, or thiol groups, as genes, proteins, cells, and microorganisms. And you have to use an external magnetic field. There have been a few strategies to make this kind of chips. The first one I'm going to talk about to you is one that they have two micropermanent magnets on two sides of the microchannel, and the separation of the beads were when they change the poles of the magnets. But this kind of strategies has problems because the magnetic force of the magnetic beads and the magnets are weak to use to separate in flow. Then another strategy that they have used is electromagnetics, but as Anita was talking before, they have the Joule heating effect, and they have to introduce to the chip an integrated cooling channel or to placing the microcoil outside the chip, making the fabrication of these chips difficult and more cost. The last strategy, and it's the one the paper used, is the soft ferromagnetics that can produce high gradients and non-uniform magnetic fields with external magnetic fields. That allowed to perform the experiment in a larger magnetic field force range. They can be controlled and have wider application. Well, it's here. This is the figure one shows the chip configuration. The chip has two layers. The upper one is made with PDMS, and the lower one with PMA. The process of separation is making in the upper layer. You can see that they have a magnetic particle solution input and one of sample solution, then a mixed channel and two channels, chambers, sorry, and a waste outlet. If you see in the down layer, you can see that it's a heating element, and this is the soft magnet. The heating element is used to, well, in this paper, they try to capture nucleic acids. And the first thing to do is to lysate the cells to release the acid, nucleic acid, and then with heat they can mix it with magnetic beads and being absorbed over the surface. Then they have to separate it using this soft magnet chamber. Well, it's a lot of mathematics as work. The thing that I want to talk about, more of this paper that I was most interested for me, was the distribution of these paramagnetic particles. Sorry, but I'm going to be up because they use soft magnets, in this case iron powder, and they inject it into the groups of mile by miniaturizing engraving machine and produce a gradient magnetic field in the separation chamber when they are magnetized by external uniform magnetic field. They proved two distribution. One was like this in blocks, and this one was little columns. When they make simulations and experimental, they see that in the bars they have a worse distribution. In general, the bits accumulated in the edge of the bars. But when they use this column distribution, they can see that there was a better homologous distribution. This is the same in another view. And the other thing that affects this distribution was the flow. They see that in the faster flow, it was better to distribution in general. Nothing more. Do you have any question? I don't know, Fernanda, if you're going to.
Yes, I can present today.
Thank you, Fernanda.
Thanks.
Let's go. Sorry, Fernanda. Luis, make me some question.
Yeah, you can answer.
Yeah, thank you. Thank you. What other question is, Luis? Very well. In my case, we are trying to separate or to capture proteins. In our case, is monoclonal antibodies. You can use magnetic beads linked with some kind of affinity ligand with affinity to your protein. For example, we are working with protein A, and the protein A, you can link it to the magnetic particles and put it in the microfluidic system and to capture these nanoparticles using the magnet. Then you have a sample, a complex sample, where you have your protein and other things. In theory, your protein is going to link to this ligand, and the rest of the proteins are going to wash up. I don't know if I answered your question. Yes, we have two approaches. One is using agarose bead with this protein A link, and the other is more to the future plans is to use nanoparticles, because agarose has some problems in not only in microchips, also in column. And I think that problems that in column are not so important can be difficult to make us more difficult to work in microchips. Then I have this backup plan. Thank you, Luis. Well, Fernanda, thank you too. You can follow.
Okay, thanks. Okay, can you see my screen?
Yes.
Yes.
Okay, thanks. Well, today I'm going to present this paper that is called Optimizing the Production of Suspension Cells Using the G-Rex M series. Basically, they are talking about this machine that is a platform to produce a range of suspension cell lines with superior cell output and with a reduction in the number of required technician interventions. Basically, they compare this machine with the 24 well plates and the flasks that are there, what we usually use in laboratories. Also, they show different aspects about this machine that they present. So as first, we can see in this graph that the first thing is that they investigated the maximal cell output per unit or surface area that could be achieved. So the first things that they do is comparing this machine with the 24 plate, and we can see that in this case, the G-Rex supports higher cell number per area, and everything they compare here by square centimeters. So in this machine, we can have more cells compared with the 24 cells, 24 wells, sorry. And also they show here the same, but in the fold expansion, we can see that is really high the number that we can obtain using this machine. In this one here, we can see how they investigated also. I'm missing one. Yeah. Here, the optimal seeding density that they should use using this machine. So they use different starting concentrations, and we can see that almost all of them, starting from 5, 2.5, 1.25, and 6.25, they can be like the results is also the same. And these experiments took at least 14 days. So in the B graph, we can see that the final concentration of cells is always the same, comparing these four concentrations. But if we take into account that the starting cells density wasn't the same, we can see that it is more efficient to use the 1.25% elevated at the 5 to have like the same final concentration of cells, but using the smallest quantity of cells starting the experiment. Then they also, here we can have, they try to identify also to determine the minimum medium volume required to support maximum cell output. So here we can see how they identify the optimal volume of medium to support this cell expansion. Here we can see how they show the maximal cell output per square centimeter that was achieved using the G-Rex devices and that were seeded with the previous results of the density that was the answer here with of 1.25, sorry. And here we can see that, for example, in B, shows that the expansion of cultures that receive a total of 10 milliliters of medium, they are always reaching like, we can put 15 or 20 and the results will be the same. So the more adequate volume will be 10 milliliters per square centimeter. And then they ask in number B if it's better to put the medium just once or in increments of 2.5 milliliters per square centimeters, or then or 2 times of 5 milliliters, or just one injection. And we can see that it is more efficient when it's just one injection of 10 milliliters per square centimeter. So here they demonstrate that 10 milliliters of medium per square centimeter administered at one time, it results in the shorter time required to achieve a maximum cell number. The next experiment that they made was to measure glucose as a surrogate for culture performance. So in this case, they measure glucose as a surrogate of culture performance, and we can see that here in A, the glucose concentration in culture medium, as they used to measure this, standard glucometer shows an inverse correlation between the cell number and the glucose concentration. So then they actually make they were able to show a formula that they developed to calculate the number of cells in the culture based on the glucose concentration in the medium. And at the end, they try this formula to see if it's actually functional, and they use a hemocytometer counting, a flow cytometer, and the glucose consumption formula. And using these 3 different approaches, they found the same concentration of the cell number. So actually, they discovered that the cell number can be calculated accurately by simply measuring glucose in cell culture supernatant, and that this formula that they use is actually correct. The next things that they made was to validate this machine that they have. And for this, they work with 3 different organizations between private enterprises and universities. And they actually took different approaches for using this machine. So actually, here we can see that it shows the schematic diagram of this G-Rex machine and the protocol that they use. So in both, the media was, the last volume media was 1,000 milliliters, which is in this case 10 milliliters per square centimeter, like they discovered before, and they practice 2 seed densities. The 1.25 per 10 elevated to 7 and 2.5 per 10 elevated to 7 cells starting in the total starting density culture. And then they did this experiment for 12 days. In number B, here we can show the comparison between the cells obtained and these 2 different investigation places. Like was the Baylor College of Medicine and this is a private company. They both use the B concentration densities. They had the same results. Also for number C, they use these different densities concentration, and in this case 3 different institutes use the machine and the results are the same. Here in D, we can see how the shows the final cell output obtained when the G-Rex device were seated at these both concentrations. And in C, we can, and in E, they show the fold expansion of the cells in the experiment described here in D. So we can see that it is always more efficient to use a lower concentration that they discovered it was the most optimal than starting with a lot of cells, and because the final density is going to be always the same. And for the last thing, they prove that this actual machine can be scalable, as they have all the cell number made in square centimeters. They try then the volume of 5 milliliters, 100 milliliters, and 500 milliliters, and play this and do different experiments. So we can see that even though the volume is different, for example, here in B, we can see how it's actually the same results, like the cell number will increase when the days of experiment changes, and it is correlated with the volume of the final volume of each machine. But we can see also here, like in C, the final cell centimeter density of cells is also the same in all the machines. And if we see the same results by fold expansion, they are equally, and the glucose concentration by they also tend to go lower. It basically is the same for the three machines that they prove here. So they now know that actually this machine can be scalable. And the last thing here, we can see how this machine is working. We can see here that they have a lot of machines connected. The number one is the pump. Number two is the 0.2 micrometer sterile filter. Number three is the medium collection button. Number four is medium line clamp. 5 and 6 is medium supplement input ports. 7 is the medium sampling port. 8 is the medium collection port. In 9, we have the medium bag. 10, the medium. And the 11 is the medium line optical detector. And in B, we can see in number 12 is the resuspended cells. 13 is the cell collection button. 14 is the cell line clamp. 15, the cell collection port. 16, the cell collection bag. 17, the harvested cells, and 18, the cell line optical detector. So the last thing that they did was to evaluate if using this collection bag was okay compared with the manual seeding, and they discovered that they can retrieve all the cells in the same density that they do in manual, and there is actually no loss of an important loss of cells in the medium bag or in the tubing that they use to connect all the machine. And that's it. Thank you.
Very well, Fernanda. Anybody has any question?
I don't have any question, but I wanted to say that it's a great guidance for the T-cell production. So I think that this paper really goes deep into the how to improve and optimize the initial cell concentration and the volume. So I think it's going to be a great guidance for you, Fernanda. Thank you for showing us this paper.
Yes, thank you, Anna. Yeah, that's why I choose it, because I think it's really accurate for what I'm doing here. So it was really useful.
Very well. If you don't have any question, we can finish this meeting. Well, thank you very much. We can see in the next meeting, Paperthon meeting. Bye-bye.
Right. Thank you, everyone. Bye-bye.
Thank you. Bye.
Gracias.
Bye. Thank you.